Hi, welcome back at the part 3 of the module 4 of our PETR3134 or Goods and Specs in Petroleum Industry. So at the part 1, we have learned on the basic fluid mechanics theory, especially the Bernoulli's law, and how we can apply the Bernoulli's law and how we can actually calculate the pipe head loss. The part 2, we have learned more specifically for the oil and gas pipelines, especially for the crude oil and for the refined uh, uh, oils. What types of equation should we use for the pipeline head loss, and how we can actually calculate the pipeline head loss using the different types like Colebrook-White equations and the at the part 1 we have learned the Dorsey-Weisbach equation, how we do that, and part 2 especially the Colebrook-White equation. And then we also have learned how we can calculate the equivalent length and etc. So and also we have learned on how to calculate the pump's NPSH. Okay, a very important part of the pump. Now at this point we will actually learn how to design petroleum facilities. Okay, so in a given petroleum industry, it's not only the petroleum industry, at any kind of chemical process industry, if you actually visit, you will find like nearly uh, 40 to 45% of the whole industry actually works on the pipe works. Okay, and other 30 to 40% would be based on like the vessels and design the vessels, and rest are like all other types of equipment. So that's exactly why pipelines and the vessels are very important. Okay, so the previous parts we actually learned how to design the pipeline and what are the design calculations we got to use, how we can actually calculate the friction loss is a very important part. Okay, but at this section we will learn on the petroleum facilities design. Okay, so let's see what types of petroleum units, what types of units we actually see at the petroleum industry. So in a petroleum production unit, we will see a lots of wellheads. Okay, so these are the production wellheads. Maybe lots of you are familiar what are the wellheads. We got the manifolds and the gathering pipelines. So these are all like the pipelines. And then for either for the gas or even the crude oil, we have lots of separators. Okay, so what are the separators? Separators, when we produce oil and gas from the reservoir, we get oil plus gas plus water all together. Okay, but the job or the duty of the separator is to separate the oil, gas, and the water. Okay, and also there are contaminants with it, and it's also remove the contaminants. Okay, so we'll actually talk extensively on these production separators. Okay, and this word like lots of separators you will actually find. Okay, and then there is the metering and storage. So storage is also another part which is very important. That's designing the storage tank. So let's learn. So these are like the pictures of the wellheads, manifolds, and gathering. Okay, separators. Let's see how it actually works. So you got the oil, gas, and water. Okay, and it goes, and there's a first stage of separator. So usually we get like 2 or 3 stage of separator. So 3-phase separators means it can separate oil, gas, and water. So okay, so the first phase we got we separated the gas, and here we got a slight portion of gas plus oil plus water. Okay, sorry, the water is actually removed in here, so we can get plus gas. So mainly we have mostly the water, a slight portion we get water, slight portion we get gas, And again at the second evaporator we got the oil, and we got the rest of the gas and rest of the water. So for instance, here the oil composition was 50%, gas was like 10%, and water was like 40%. Okay, at the first stage we will get oil in here is like 80%. Okay, and gas will get like 5%, and the water would be like rest of the amount, for instance like the 15%. And here after that we'll get something like 99% water, sorry, oil. Okay, and rest of the water and gas would be removed. Okay, so this is how these stage operators stage separators actually works. Specifications for the separators. So for the oil and gas separator we have API 12J. So this is the spec we should follow. So what is a separator? A separator is a vessel used in field to remove the well stream liquids from gas components. Okay, a separator may be either 2 or 3 phase. A 2-phase separator removes the total liquid from the gas, while 3-phase separator also remove free water from the hydrocarbon liquid. Okay, so at the separator, if you actually go through the API specification how to design a separator, so there are several factors are very important. So number one factor is the operating pressure of the separator. So what would be the operating pressure of the separator you should actually follow. Okay, so the pressure of the vessel during the normal operation should not exceed the MAWP, or maximum allowable operating pressure. So how we can calculate maximum allowable operating pressure? We will see that, remember. Okay, the operating pressure of a separator should not exceed MAWP. That means it would be less or equal of MAWP. All right, so MAWP we will actually determine through or calculate using the ASME code. Okay, remember that. Material selection, again the ASME code BPVC, or boiler and pressure vessel code. Using this we can actually determine the material, what types of material we should actually use. For instance, if the fluid is corrosive, we should use different types of material, rather if it is not corrosive at all. Okay, so based on the API or NSCE publication, we can check the corrosivity and the type of material that conform with the ASME code. Okay, the consideration should also be given related with the weight loss, sulfide stress crack, or SCC, or the chloride stress cracking. Okay, or other forms of corrosion. Okay, types and pressure and temperature rating. So probably you already know about the pressure and temperature rating from we use like pipeline components use the pressure and temperature rating. Okay, but similarly the pressure vessels also got the pressure and temperature rating. Okay, so also what would be the specification? Like it should be vertical, it should be horizontal, or spherical. These are very important. So the size and type is very important, we should actually select. Okay, and also by the MAWP rating. So we'll actually see that how we actually calculate it. Okay, but remember these are very important factors. The size, type, pressure and temperature rating is very important factor. Okay, so this is example how the separators actually look like, and here is the working principle. So please go through this link and you can actually see the animation how the separator actually works. So how it actually works, we got oil plus gas plus water and some contamination or dirts. Okay, Remember what is this one? We have covered at the last class, remember? This is the PRV, right? So here is the vapor, okay, and this is the oil, and this is the water. So that's how it's actually separated. So there is something we call retention time. So we put the oil, gas and water all together, and then we give a specific time. Since the gas got higher volatility and lower specific gravity, so gas will actually go up and it will go out. Since the oil, water actually got more dense. Water specific gravity is higher, so after a certain time the water will be settled down and it will be removed through here. Sorry, the outlet is here, and oil, it will float on the top of the water, right? And after a specific time it will be removed here. So all the whole operation will be done by the use of gravity. Okay, so sometimes it's also known as gravity settling tank, but gravity settling tank, we use that terminology for a different types, especially for the solid contamination and liquid separation. We use the gravity settling tank, but the principle is similar, very similar with the gravity settling tank with this separator. Okay, so this is how this oil and gas separator actually works. So this is the picture from the API specification. Okay, so that's very similar principle in here, as you can see. Components, what are the components actually we have for the separator? Please go through this component, like the primary separating section, what is the secondary separating section, and the liquid accumulating section. We got mist extraction section, and definitely process and instrumentational control, or like the process control, the relief valve, PRV, and other controls. Okay, and the sensors, like definitely we'll have a level sensor, we have a pressure sensor, and we have a temperature sensor, and inlet shut-in valve. Okay, so these are the control and accessories we have. Separator design, should it be vertical or horizontal? It depends on many other factors. What are the factors we should actually use to choose? It would be spherical or horizontal or the vertical one. Okay, nowadays you will less likely see the spherical one. During like 1960s or 70s, there are lots of spherical one, but now usually we use the either vertical or the horizontal, depends on the different types of fluid. For instance, for the light crude oil, we usually use the horizontal one, but for the heavy crude oil, we use the vertical. Okay, now during the offshore operation, we usually choose the vertical one. Why? Anyone? Because at the offshore operation we have a space constraint, right? So if we choose vertical, it takes less area than the horizontal, right? So that's why we choose the vertical design. Okay, so these are the inlets we have for the vertical and horizontal separator. Remember all this is important. Okay, what are the units we got in here? Now this is the pros and cons of the properties of the factors to design the separator for the horizontals. Okay, if the shape is horizontal, so these are the factors, and for the vertical, okay, these are the factors. If these factors satisfy, we choose the vertical separator, and for these types of factors we choose horizontal separator. Okay, design calculation. So sizing of two-phase oil gas separator. So let's assume we have two-phase, because the three-phase would be way more complicated. That's why we just choose in this case two-phase. Okay, so the sizing of two-phase oil gas separator, how can we size that? So the minimum, this is the formula for the maximum allowable superficial velocity of gas operating condition. Okay, VA is equal to K of dL minus dG by dG. Here dL is the density of liquid, dG is the density of gas, K is the design factor, and VA is the maximum allowable velocity for the gas. Retention time, remember retention time. So what is that actually? Like here is the separator, for instance. We put oil and gas. Okay, the gas will go out, and after a certain time the oil will stay, and then the oil will also go out. Now if we know the velocity of the gas here, the maximum allowable superficial velocity of the gas, okay, how much gas actually it will actually create, like I mean here the gas phase and here is the oil. Okay, so after a certain time the liquid, the crude oil will, I mean the dissolved gas in the crude oil will go out, and this gas chamber, I mean this empty area of the separator will fill out the gas, and the gas will go out. So we will design a separator based on how much volume of gas it can actually handle. Okay, so that's exactly why we calculate the VA at first, then we'll calculate the retention time. Okay, and how we can calculate the retention time? A good separation requires sufficient time to obtain equilibrium condition between the liquid and gas phase, okay, at the temperature and the pressure of the separator. So W, which is the liquid capacity, barrel per day, is equal to 1440 times V, the liquid settling volume, divided by the retention time. So T is the retention time. That means T is equal to 1440 times V by W. Okay, so if we know the liquid capacity, if we know like the liquid settling volume, okay, then we can actually calculate the retention time from here. Okay, and K factor. So for vertical, for the height of 10 feet, the K factor would be this. For the height of 5 feet, for the height of 10 feet, this is the K factor. Okay, and for the horizontal, these are the values for the K factor. For spherical, the K factor is be in between this and this. Typical retention time. The typical retention time of a two-phase separator depends on the specific gravity of the oil. Now, usually we use the API gravity instead of specific gravity. Okay, and as you know, API gravity and specific gravity is inversely proportional. That means for the heavy oil, the API gravity would be lower, and for light crude oil, the API gravity would be higher. Okay, so for the API gravity 35, the typical retention time is 1 minute. That means for the light crude oil it is 1 minute. That makes sense, right? Because if the crude oil is lighter, then it will evaporate. It will release the gas dissolved in the crude oil will take less time. But if the crude oil is heavier, then it will take more time. So the retention time will take more. So let's do a math, and then we can actually we will actually know how to design it simply. Okay, so let's design a separator, the vertical two-phase separator. Okay, so find the maximum allowable superficial velocity and liquid capacity for the separator. So if it's a two-phase separator, so the input would be oil and gas, we should calculate this gas velocity, okay, and also the liquid capacity, how much liquid it can actually have. So how much liquid it could actually hold. Okay, so what are the information we have? We have the gas rate is 25 mmscfd, that means billion standard cubic feet per day. Gas specific gravity 0.6, gas compressibility factor 0.84, gas density, molecular weight, oil rate is 3000 barrel per day, oil density API, okay, 51.5, 40 degree API, that means 51.5 pound per feet. Oil operating pressure 800 psi, which is very high pressure. Operating temperature 80 degree Fahrenheit, and K factor is given, and liquid retention time 1 minute. Okay, so let's calculate. So step 1, what we will actually do first, we will assume the height is 10 feet. Why? Because have you seen this chart here? Here is the chart. Okay, now let's assume the height of the separator is 10 feet and 30% liquid full. Okay, then we should actually estimate the maximum allowable superficial velocity of gas, is k equal to 0.3. So we know this chart, from this chart here we know the 10 and the K factor. Okay, so we'll put all this value dl dg, and then we'll actually calculate the VA. Okay, and VA we'll just assume is 0.3. Why? Because it's kind of like in between the average. Okay, that's exactly why. I mean, it's 0.1 to 0.35. We assumed it's a 0.3, and then we'll calculate the VA. Now the actual volumetric flow rate, how we'll actually do that? The calculator is given 25 mmcfd. This is very important, this conversion factor. That means this amount of standard cubic feet per day, LB per mole, standard cubic feet per mole, second per day, and we have calculated the volumetric flow rate. That means cubic feet per second. Okay, and now the step 2, let's determine the minimum gas flow rate. Okay, how will determine that? Gas flow area, flow rate area, here, this area. Okay, how will calculate that? That is, area is equal to flow rate divided by velocity. We know the flow rate and we know the velocity from here. Okay, so we calculate the area of the gas flow. Now when we know the area, we can determine the minimum ID. That means we have calculated the minimum ID near, it's a little bit slightly more than 2 feet. That means now we have calculated the internal diameter is like 2 feet. Okay, now let's estimate the liquid settling volume, and let's assume the diameter of the pipeline is 30 inch. Okay, next let's do the standard diameter. That means we calculated minimum area diameter is 27 inch. So 27 inch is like, I mean, not the standard size, so we assumed it's like 30 inch. Okay, so if we assume it's 30 inch, so the volume would be 2.62 barrel. Okay, and finally we can calculate the liquid capacity using the retention time, and retention time T equal to 1 minute. So W is equal to this. So that's how we can calculate the capacity of the separator. Okay, so I know like there are lots of like unit conversion, that like the real Problem is very simple, but there is lots of unit conversion involved, so be prepared for that. Okay. um, Remember at the earlier slides we talked about the we have talked about this one, this MAWP. Okay, so here this is very important. We'll actually discuss on the MAWP here. Okay, so let's do a problem and then we can actually solve it through the problem. So the problem is determine the separators wall thickness. Okay, so we have decided, like, I mean, what would be for, let's assume in the previous example we have decided, like, I mean, what would be the liquid capacity and flow rate for the separator. So what would be the thickness, or like maximum pressure, wall thickness or the maximum pressure of the separator. Okay, let's do that example. So the ASME code, the pressure vessel code, the section 8 division 1, for the ellipsoidal head we should use this formula to calculate the minimum thickness, and for hemispherical head we should use this formula. Okay, so this is the hemispherical head, looks like a bullet, like, I mean, the if you draw the circle and make it half, this is the hemispherical set. So there are lots of pressure vessel you'll see like this. Okay, so this is the hemispherical head, and this is ellipsoidal head. That means it looks like more like, I mean, rounded ellipsoidal, and the pressure vessel is like that. Okay, so this is ellipsoidal head, and this is like hemispherical head is more like round in shape. Okay, more like round in shape in here. So these are like the two different pressure vessel type we can actually design, and for these two different types we have these two different formulas. Okay, so most of the production facility, the vessels are usually ellipsoidal head because it's less expensive and take less room than hemispherical heads, but there are some hemispherical heads too. So these are the ellipsoidal heads. This is how it looks like, you see, and this is the hemispherical head. Okay, all right, so these are the design. So this is the hemispherical head, this is the ellipsoidal head design. Okay, now at the previous example it's the same design conditions we have. Okay, now let's assume our separator is horizontal and ellipsoidal head. Okay, so if these informations are given, so how we can actually calculate the minimum thickness. So let's we know that these two equations. First step, we should select what types of equation we use. Since we use the ellipsoidal head, we should use this equation, right? And then we should select the material type. What are the usual material type we use? Carbon steel, remember? So we should use the carbon steel, or sometimes we can use actually high alloy steel plates too. Okay, now based on the operating pressure or operating temperature, metal grade, we would determine the allowable stress value, maximum allowable stress. Okay, from this table 12.3. so these are the MAOP, or like maximum allowable stress is actually given, and we'll plug the variable at the right equation and we can solve the equation. Okay, so these are very simple steps. So first step, selecting the right equation. Second step, selecting the right material. Third step, pressure and temperature conditions. Okay, fourth step, we'll put all this information to the right equation, and then fifth step, solve the equation. So the first step, we know ellipsoidal, material carbon steel, temperature 80°F, grade 60, so the maximum allowable stress would be 20,000 psi. We can calculate this from here. Okay, I will actually upload the table for you. Then we calculate the T, or the thickness of the pipeline. Okay, now this is how we calculate the thickness of the of the um, of the pressure vessel. Now it is very similar with the, if you see, it's a very similar fashion we use the for the pipeline thickness. Remember, we calculate like the pipeline thickness. It's the very similar fashion. However, in this case we use a systematic methodology to calculate the um, the thickness for a pressure vessel. So this is an example for the separator. In case of boiler or any kind of pressure vessel, including the storage tank, the formula is same. You can use the same formula to design the case, like to calculate the thickness of the material. Okay, so this would be all about today's lecture. So again, let's recur about the whole part. So the first part, we have learned on the pressure drop calculations, so the Bernoulli's equations, friction loss, especially we have learned the friction loss, how to use the Moore's diagram, Darcy-Weisbach equation, and everything like that. The second part, we use the Colbert-White equation and Hazen-Williams equation. We know how to calculate the equivalent length, okay, and then using the Hazen-Williams equation, how we calculate the head loss, and then we know how to calculate the total dynamic head, and very important one, the NPSH. Okay, and we have calculated how to calculate the NPSH. And at the part 3, we have learned on the separator designs, how the separator design work, what are the specifications we should use, and how we can design a separator or a pressure vessel step by step. Okay, so that's how we learned all the information on that. So this would be all, folks. This would be the syllabus, I mean the for all the parts of the module 4. So if you got any question, please let me know. And I know that there are lots of maths in here, but please practice the maths so that you can actually have more idea on this. Okay, all right, take care, and talk with you soon at the live session. Bye.